Let's have a look at the product rule. And the chain rule. So suppose we have this awkward function. We know how to differentiate x squared, we know how to differentiate sine x, but how to differentiate x squared sine x. So let's look at the general case where we have y equaling some function of x multiplied by another function of x. So we could think of y as the area where f of x is the horizontal length and g of x is the vertical length. So I'm going to mark off that as f of x. That as g of x. And then this area is f of x, g of x. So suppose x changes by delta x. So this would be f of x plus delta x. And we could call this distance delta f. And similarly, we get a new g value. And that's delta g, that distance there. So what's our new area? Well, this is f of x delta g. And this is g of x delta f. So the change in y is equal to f of x delta g plus g of x delta f plus that little rectangle. So if we divide both sides by our change in x, maybe we should note that x is going to x plus change in x. So what happens as the change in x shrinks to 0? So as change in x shrinks to 0, this becomes dy by dx. This becomes dg by dx. df by dx. And this third part we could either break it into delta f times delta g by delta x, or delta g delta f by delta x. The deal is that as delta x shrinks to 0, these are just giving us our derivatives for f and g. So here's our f, and here's our g. And at a particular x, so here's change in f, here's change in x, and here's change in g, and here's change in x. So we are assuming that as change in x shrinks to 0, both change in f by change in x and change in g by change in x are going to approach certain values, whatever the slope is at this point and this point. So as delta x shrinks to 0, this last term is going to disappear. Whichever way you look at it, it's either delta f times some number, whatever the slope of g is at x, or it's delta g times, again, some fixed number, whatever the slope of f is at x. Either way, it's going to dwindle to 0. So we could rewrite this as f of x, g of x differentiated is f of x, g dash of x plus g of x, f dash of x. Or we could even just write fg dashed is f dash g plus g dash f. And that is our product rule. So solving our original example, we've got y equals x squared sine x. So f of x equals x squared, g of x equals sine x. F dash of x will therefore be 2x. And g of x dashed will be cos x. So y dash of x equals f dash of x, g of x, g dash of x, f of x, which is Okay, let's move on to the chain rule. Suppose a bullet moves 3 times faster than an arrow. So we have bullet over arrow equals 3. And also an arrow, say, moves twice as fast as a tennis ball. So arrow divided by tennis ball is equal to 2. And the question is, what is the speed of a bullet relative to a tennis ball? And obviously a bullet moves 6 times faster than a tennis ball because it's just 3 times 2. So what's going on is our bullet ratio to that of a tennis ball is equal to bullet to arrow multiplied by arrow to tennis ball. And that's your basic chain rule. It's saying if you have an x and a function taking it to y, let's call that f, and another function taking it to z, let's call that g, then we want to know if we change x by a little bit, how much does z change? So the change in z by the change in x is equal to the change in z by the change in y multiplied by the change in y by the change in x. Roughly equal to. It's in the limit as these values shrink to 0 that equality becomes exact. So in the limit, as change in x tends to 0, this becomes dz by dx equals dz by dy times dy by dx. And this is our chain rule. Another way of writing it would be to say we've got y equals f of x, and we've got z equals g of y equals g of f of x, and we're interested in differentiating that g with respect to x. That's going to equal, well, dy by dx is just f dash of x and dz by dy is just g dash of y. Notice that the Leibniz notation using d's is better than the dash notation here, because the dash notation doesn't explicitly say what we're differentiating to. This dash is with respect to y, and y you can see is the dependent variable. This is with respect to x, and x is the dependent variable. So you need to use your common sense a bit to see what's going on. This way of writing would be unambiguous. So we could say differentiating with respect to x, g of f of x is equal to d by dx of f multiplied by dg by dy. I'm just writing the same thing different ways. If you're going to remember one thing, remember this. If you don't want to remember one thing, figure it out from scratch using arrows and tennis balls. Another interesting way of seeing it might be to use a 3D graph. So you've got your point x, you've got a function f that maps x to y, and you've got a function g that maps y to z. So we're saying if we perturb x by an amount delta x, then y will change by an amount delta y, and z will change by an amount delta z. This is awkward. My curve is kind of really steep, so it's going to make the picture messy. So let me adjust that. So that's change in y, and that's change in z, and that's a right angle. This is a right angle. So our change in x causes a change in y, which then causes a change in z, and so now we're interested in that change in z as a ratio of our change in x, which we can use our third plane for. So this was our change in x, and this is our change in z, and this is our slope dz by dx. And you can imagine as these delta values get very small, the functions are going to approach straight lines. At the end of the video, we'll look again at this diagram and see how to make sense of it, see how it gives some intuition behind what's really going on with the chain rule. So let's work through an example of using the chain rule. Suppose we've got y equals sine of x squared. Okay, that's just sine. Let's use z to keep our symbols consistent. Z equals sine of x squared, which is sine of y, where y equals x squared. So z equals sine y gives us dz by dy is just cos y, and y equals x squared gives us dy by dx equals 2x. So what is the change in z for a given change in x? What's the slope on that z as a function of x curve? It's just dz by dy by dy by dx. Multiplied by, I should have said. Which is cos of y times 2x, which is 2x cos x squared. Okay, done. Let's prove the chain rule. So we know that our delta y by delta x tends to f dash at x as delta x tends to 0. So our delta y by delta x is equal to f dash of x plus some epsilon that depends on x, and this epsilon tends to 0 as delta x tends to 0. Let's call that epsilon 1. Similarly, change in z by change in y is equal to g dash of y plus epsilon 2 of y. So, what is delta y by delta x times delta z by delta y? It's just these two things multiplied. And as delta x tends to 0, both epsilon 1 and epsilon 2 tend to 0, but these are fixed values, g dash of y and f dash of x, so therefore this whole thing tends to 0, and we can strike it out, and we're left with this, which is this formulation down here. But what's happening on the left-hand side? Well, these are fractions So this just cancels and we're left with delta z by delta x. And so taking limit as delta x tends to 0, we have dz by dx, aka g of f of x dashed equaling f dash of x g dashed of y. Done. Finally, let's return to this 3D representation and try and extract some meaning out of it. Can you see that if you double dz by dy, so imagine delta z doubling in length, but delta y, the height, staying the same, then that's just going to double the length of this triangle here, so it's going to double dz by dx. So delta z by delta x is proportional to delta z by delta y. And similarly, if delta y by delta x doubles, you can imagine replacing that height with twice that height. It's going to, top of the triangle is going to project to here, which is going to project to, assuming this is now a straight line, twice as far along. So again, you'll get a doubling of delta z. So again, if this height doubles, we get a doubling of delta z. Delta x is staying the same, so delta z by delta x has also doubled. So delta z by delta x is also proportional to delta y by delta x. And so intuitively, this formulation is looking correct.